Hello, Hackaday. I'm here at the lab with the Telepresence robot for the lab mice, and it's all set up right here. And I just wanted to show you what we got cooking. This is the trackball. It's suspended in an air bed, so this is a custom printed base that we're pumping air into. And this is a very low inertia, which makes it much easier for the mouse to move. This is the head plate, which will fix the head of the mouse while it is under the microscope. And then these two USB mice fixed here are capturing all the rotation data of the trackball. And this is being sent over to a Raspberry Pi. It's being captured by a Raspberry Pi, which uses a 900 megahertz XB to transmit motion commands to the Telepresence robot right here. It was 900 megahertz because we had some specific length requirements or transmission length requirements. And then this video stream is then in turn sent back to this display, this heads-up display in front of the mouse. So it will display the video with very low latency, as well as save and extract the video, all of its frames, and all of its timestamps for post-processing. This also captures, it not only transmits but also saves the motion data. So we have a very well-controlled parameter space because we know what the mouse is seeing. We can see we can capture how it's behaving, or we can capture its motions, and we can also capture its brain activity. So we can really start to, well, not me, it's way above my pay grade, but the idea is we'll be able to put together a very accurate image of how that all correlates. So just to show how it all works, I made a little GUI it's a little bit of a Rick and Morty reference. And this is using Tkinter. I don't know what it is. TK. I don't know how you pronounce it. I really regret using this, but so we'll just make sure everything's connected and on the network. We can start the video stream, and here you'll see it. There are a couple different resolution options, but right now we're going for lowest possible latency, so we're just doing 640 by 480. We can start the robot so it's ready to receive motion commands, and that does a little dance when it's on. Turn on the air for the trackball, and now it's free to move. And let's start transmitting coordinates. So now we have the robot's perspective of us, and we can control it with the ball. It's a very interesting problem because we have to determine what's the most intuitive way for the ball to control the robot, for the mouse to control the robot from the ball. So while the robot has 3 degrees of freedom, the rat really does not, because it can really only face the front hemisphere of the ball. Alright, it's a little tricky to capture all of this in one frame and control it with the other hand, but I'll do my best. So here we have the trackball motion, and pulling it back should result in a forward motion. A lot of the tricky processing, a lot of the tricky geometry is being handled in Python. So we have to figure out how to go from the encoder inputs on the mice, on the optical mice, to an absolute position of the robot, and then back to encoder counts on the robot's wheels. So a lot that's being handled in Python, although I didn't find any really mainstream libraries. So once we're done with the video stream, or with the whole testing process rather, there's a Ubuntu PC that kind of pulls all the data together. So we can turn off the trackball, the robot, and the video stream. And now all this data is pulled onto a separate hard drive. So here are the videos. They're all dated, and they're automatically pulled off into individual frames. It'll take a while to load because it captures at 30 frames a second, and testing can last for hours. Unfortunately, I'm not capturing the metadata of the timestamps of the frames themselves when they're displayed. Or rather, unfortunately, we're not capturing the time of the frames display directly. Instead, I'm imposing a timestamp on the image and then using the Tesseract wrapper on Python to extract that timestamp from each picture individually, which takes some time. And then likewise we have all of the trackball data. Of course we have to import it as a CSV. So this can show us, this is a dry run obviously, the change in time between each update, the arc length along each axis, and the corresponding bot output.